Looks like we're ready to get started. So, I'm John Healy. This is all joint work with Leland McInnes, who some of you may have seen yesterday, and Colin Weir. We're mathematicians and researchers at the Tutt Institute for Mathematics and Computing in Ottawa, Canada. We're a small research institute focused on sort of foundational and fundamental data science algorithms, amongst other things. This talk used to be called Map All the Things, based on an algorithm we wrote called UMAP. I've rebranded it Embed All the Things in hopes of not confusing the cartographers in the crowd. I apologize in advance for tricking you all into coming if you are in fact here. Very sorry. So what do I mean by all the things? I'm going to start off, we're going to talk about fixed width numeric data. This is the traditional data that data scientists have been dealing with for years and years now. We'll get us ramped up on that, and I'm going to transition into variable length categorical data, which is typically slightly harder to do for embedding. We're going to spend some time talking about that, and finally I'm going to transition into embedding words and documents. All right, because reproducibility matters, you can find both the slides and all of the notebooks that I used to do most of these embeddings on this GitHub page. Feel free to download them and grab them and run them. My hope is that by the end of this talk, you'll be able to clone that repo, load those notebooks, and pivot them and use them to embed your data and do real world things using sort of the topology and the embedding techniques on your problems. All right. Last note, I've got a couple of little snippets of code that are pasted throughout the talk. They're really pictures of code. Again, the notebooks exist and are reasonably well documented. You probably don't need to be scribbling down lines of code as you go through either. All right, start off. What is an embedding? If I'm going to ask you to embed all the things, I really need to tell you what an embedding is. So this is an embedding, or a galaxy exploding. I'm never sure which. Either way, an embedding is a numerical representation of your data with meaningful distances between your points. So this one is, you want a nice low dimensional representation, and the reason you want to do this typically is to explore or look at your data. This is a two-dimensional representation where each of those dots is an individual point. I've used the lovely data shader to fold those points on top of each other so that the very bright or intense regions of the space are the ones that have many, many points in a very close region. So you could think of that as those are clusters or natural groupings of your data, regions with lots and lots of points in them. Okay, what did I just say? I said an embedding is a numeric representation of your data along with the distance. You need both in order to have an embedding. If you're going to do unsupervised learning on anything, you have either explicitly or implicitly chosen a distance function for your data. I'm going to argue that that choice should always be explicit. So, why do you care? Why would you actually want to go about doing any of this stuff and embedding any of your data in the first place? I hinted at the last slide, unsupervised learning is the right answer. So another phrase you could use to describe unsupervised learning is data science with no labels. If you have labels or things you would like to predict, you're doing supervised learning. If you don't have any of that, you have to use unsupervised learning. Typical tasks in unsupervised learning are grouping your data, looking for outliers or anomalies in your data, or exploring your data and visualizing it and looking to see what's going on and if there are complex relationships inside your data. So, again, we said we want a numerical representation of our data. Why? Because math. So we want to be able to do math on our data. Math really likes numbers. And I said you need a distance measure because I have no labels. So math and no labels, I'm going to do unsupervised learning, I'm going to do embedding. Now, data. We're doing data science here. Everyone here is a data scientist. I can't do data science without data. Doing data science without data is like making beer without water or swimming without water, whatever floats your boat. Let's introduce some data. You should always select data you really care about, you really like, you're really interested in and analyzing. That's why I chose beer. I brew beer with a friend. I find beer both interesting and delicious. So we're going to spend some time analyzing it. This is a Kaggle beer review data set that you can go and download from this URL right now and do your own analysis. All right, we download it, we load it up into a pandas data frame, we do a head, we transpose that, we look at the number of rows. This gives you the first couple of rows of our data, and you can see we've got lots of interesting fields, ways to slice and dice and explore the data to answer lots of really interesting questions we might want to ask about beer. So I'm going to use this data to show you lots of different ways to slice, dice, and embed it to answer a variety of different questions. All right. I'd like to think of each of these ways of slicing, dicing, and embedding your data as different lenses through which you can look at your data. Every one of those lenses or every one of those embeddings is going to tell you something different about your data. And every one of them is going to be wrong, but some of them are going to be useful. All right. Let's start with a traditional kind of lens over top of our data. Fixed width numerical data. This is kind of data that data scientists have been doing since the dawn of time, or at least the dawn of statistics. The first thing we need to do is select what we're going to embed, the thing we care about. Very natural choices for that would be beer. You can embed beer into a vector space. That would be fun. We could talk about beer styles instead. You can embed beer styles into a vector space. We could look at reviewers. So we have reviewers who reviewed the individual beers. You could embed them into a vector space if you were more interested in who was reviewing beers in your data set. Or breweries. We have the breweries that made the beer. We can talk about exploring relationships amongst breweries. That choice depends on the question you're trying to answer and the story you're trying to tell. All right, for now, we're going to choose to embed beer styles. The next question is with respect to what features? So in other words, what makes two beer styles similar? There's some obvious choices. We have some numerical features. We all like numerical features because we've been doing this since sort of undergrad data science. Like, yep, I know stuff I can do with numbers. Fantastic. I am going to select, review aroma, appearance, palate, and taste, and say, I think that two beer styles are going to be similar if they get sort of similar rankings in these sort of categories. I'm going to leave out the overall beer style for now. We'll get back to that later. You have a problem, though. Each of those variables is a distribution and not a number. So for American IPAs, for example, if you look at the taste review, it's a distribution of 117,000 different reviews, and that's that distribution. That's hard to deal with. We need a number to represent the taste for the beer style. Enter pandas group by. So, since we need one row per thing we're interested in this case beer style, we're going to group by beer style. That is going to collapse down and emit one row per beer style. Now, we need to tell it how to summarize those 114,000 numbers that are associated with taste for that beer style. And so we pass into this group by object the columns we care about, or the features we care about, and how we like to group or aggregate them. In this case, I chose mean. It's straightforward, it's simple. You could have used median, you could have used truncated mean, you could have used percentiles. There's lots of other things you could use. This makes things clean and simple. You'll notice there are a number of other columns we've included as well. At the top, there's some categorical columns like beer name and beer brewery name. Means don't make a lot of sense on these categorical variables or strings or names. So instead, we're just going to take the most frequently occurring one there. Now, those are what I'm going to call background features. We're going to use them for like labeling things and enhancing in our data after on, but we're not going to make use of them as part of the actual embedding. All right, so I have a 4 tuple of features that I care about. I've done my group by. I've collapsed down to 104 rows for my 1.5 million reviews. There aren't all that many beer styles in the data, it turns out. And we're going to use a subset of this data, so the beer reviews or beer styles at the top, to be the columns that are going to be our numerical representation of our data. All right. Now we've chosen the representation. The other thing I said you needed before you have an embedding is a distance. This is where it gets hard. There's an awful lot of potential distance measures to choose from. What you choose is ultimately going to determine your results. It's going to determine which points are similar to each other. So this is going to come down to you either knowing something about your feature space or having an evaluative task that you can try these things on and see how well it does. In the absence of any extra knowledge, I'm going to recommend a good rule of thumb is Euclidean. which is L2 distance, Manhattan, which is L1 distance, or cosine distance, which is sort of an angular distance. These are the non-controversial go-to distance measures you won't have a hard time arguing with, but more importantly, they're distance measures that are easy for you to understand. And if you have to decide fundamentally, sort of as an axiom, that this is a meaningful distance measure on my feature space, you need to understand how that distance measure is going to behave on your feature space. Now, the first step there is looking at your data. So look at your data. Check your columns. See that they're on the same scales so that distance across those scales is meaningful. In this case, they are. Notice we didn't include ABV, or alcohol by volume, on this representation, even though it's a number. And, you know, we could embed things with numbers. But if you had looked at that, I didn't include it because, one, I don't know the difference, what the relationship is between 3 and 4 on a rating scale versus 3% and 4% on an alcohol by volume scale. Those are totally different and totally arbitrarily comparable scales. So it's not a natural one to include in this case. Additionally, if I'd included ABV, you can see that it's on a wildly different scale. You'd also have this problem if appearance was rated out of 100 instead of rated out of 5. Those large scale variables would swamp my distance measure, and that would be the only thing I would be detecting. So you need your variables to be on similar scales. An common way to deal with this is sklearn. You can normalize or standardize your data to be looking at standard deviations instead of looking at the absolute scores. But it turns out we don't need to do that in this case. Everything is on a very nice, very similar scale. I look at this, I decide L1 distance, or Manhattan distance, makes a lot of sense here, which is going to be the sum of the difference between these 4 coordinates. I now have a distance measure, and now I have an embedding. Beer styles are a vector of their mean scores along with Manhattan distance. This is an embedding. I can be done right now. If what I want to do is clustering or outlier detection, you can go ahead and do that. I would have a strong preference for HDBScan. That's because we wrote the fast HDBScan algorithm in scikit-learn contrib. We quite like it. It's a good first clustering algorithm to run in your data. It'll work on that 4-dimensional data. But it might not work on really high-dimensional data. And another thing you might want to do instead of clustering is look at your data. So how would you go about looking at very high-dimensional data, or potentially 4-dimensional data even? Well, enter dimension reduction. There's lots of reasons you might want to do dimension reduction. Maybe somebody at a PyData talk told you to look at your data. That's an excellent reason to do it. Doing dimension reduction works there. You might want to visualize it to look for complex relationships in your data. Maybe your data is really high dimensional and your clustering algorithm doesn't scale to really high dimensional data. Maybe your clustering algorithm doesn't support the distance measure you decided was true and you really wanted to use. We're going to use a dimension reduction algorithm called UMAP to find a low-dimensional Euclidean space that approximates the distance function you really cared about. All right. Why UMAP, I hear you ask? Well, there are a few good dimension reduction algorithms out there. The popular ones are PCA and TS&E, both solid algorithms. They have their place. The pithy answer to why we're using UMAP is that we wrote UMAP, and so we like it. The longer answer is the reason we developed it was we needed a fast, scalable, nonlinear dimension reduction technique that had strong mathematical underpinnings. All right. For those who attended Leland McInnes's talk yesterday, you already completely understand UMAP, and the next 2 minutes are going to be slightly boring for you. For the rest, I'm going to give you the 1,000-foot overview of UMAP, so you have sort of a vague idea of what it's going to do, and then we're going to go and make use of it. So, at its heart, UMAP is a manifold learning technique. That is, they're going to draw an edge from every point to its set of nearest neighbors. We're going to look at that graph structure. We're going to try to unroll that graph structure into a low-dimensional space and lay it down there. There are a few more details to keep in mind, but that's really the important part of what UMAP is doing. It's preserving this topological structure in your data. All right. The key, though, is that it's a locality preserving technique. If your data isn't naturally 2-dimensional, any dimension reduction algorithm is going to be forced to make sacrifices when embedding in 2 dimensions. This is a picture of a mammoth. It's a 3-dimensional skeleton of a mammoth. The data points, that doesn't fold down into 2 dimensions very well, but you can see we've preserved a lot of the local structure here. UMAP works very hard to preserve that local structure but the sacrifice it's making is global structure. So this is an excerpt from a great article that Andy Cohen and Adam Pierce from Google wrote about the algorithm. The link is above. It's got lots of sliders and widgets and parameter tools that you can use to explore how and why the algorithm works and what it does on your various data sets. It's a really nice place to get started with understanding how UMap's going to behave on real data. All right. There's a lot of documentation. Read the docs. Feel free to pop over those and give those a read. That's easy to find via Google. If you want to get into a little more theory, my colleague Leland McInnes gave an excellent SciPy talk in 2018 on UMap, or at PyData in LA in 2019, yesterday. It's also good. All right, or you could just pip install it right now and start using it on your data and see how it does. All right. Back to looking at your data. Now we have a dimension reduction algorithm. I'd like to use it. Let's use it to look at our data. Sweet, that's visible. All right, so we ran UMap on the numeric data I just showed you with the Manhattan distance. That was the embedding we chose. We found a two-dimensional Euclidean space for it. And we specified the metric directly in the UMap algorithm there. You can see where we pass it in. L1 and Manhattan are the same metric. Interestingly, it looks like this data lives on what I would call a one-dimensional manifold. All right? It lives on one smooth arc in that space. So now, a quick note to be warned on UMap, the XY coordinates here aren't meaningful in any particular way. We have tried to preserve the topological structure of the data. So here, that could have come off as a sinusoidal curve, it could have come off as a straight line, it could have come off as a U or a C. All of those have the same, what I'm going to call topological structure, or local relationships being preserved. So don't place a lot of faith in the XY coordinates themselves. Look at the structure that you're seeing within the data. Here, I've colored it by SRM, which is standard reference method, which is just a way to determine what a beer color is, because I thought that would be really insightful on looking at the data, and it proves to not have anything to do with the manifold we've learned, and that makes us a little sad. But that's okay. We switch back and color by something different. We're going to color by overall beer rating. We didn't use that in our embedding. We held it back, and we're curious to see how it might relate, and we are perhaps not entirely surprised that that one-dimensional manifold lines up almost perfectly with the overall score of the beer, or the overall ranking of those beer styles. So the next thing I'm going to do here is I would do an interactive hover tool with bokeh, enhance each of the data points with extra information, and then start exploring what those points actually are. So I did that, and I added the labels to here because hover tools and bokeh are hard to do inside a slideshow. And it turns out that this is what beer advocate reviewers think of beer styles. In the far bottom left corner, you've got light lagers, low alcohol beers, these sorts of things. They tend to be ranked very poorly by beer advocate users. So poorly, they've torn the manifold and they're living off in a little cluster all on their own in the bottom left corner. When you jump into the actual sort of manifold itself, you get into the sort of standard lagers, and then you wander along the lager, getting more and more popular as you go, and you hit porters and stouts, and then you wander down into the bottom right corner of the things people really, really like on beer advocates, and you end up getting, red ales and imperial IPAs and quadruples and lambics. These are big, bold, very flavorful beers, which all have a high alcohol by volume ratio, but I'm sure that has nothing to do with anything. It's all about the flavor. All right. So what if you didn't have nice numeric features to represent your data? What if instead you had categorical data? All right. Let's take a different lens on the data to illustrate how we might go about dealing with that. All right. Let's say we're still interested in beer style. That's easy. But now we want to say beer styles are similar if lots of the same people review that beer style. All right? So this isn't how you thought about it. This isn't with the ranking. This is if you all looked at the same beer style. All right. That's easy enough to do. Let's pivot. We've done the group by before. You said, all right, well, what do we want to, what are our points? Beer style. We're going to group by beer style. Now, what do we want? Reviewer profile. The trick here is going to be in our aggregator. We've got a whole bunch of extra variables again because we're going to want to enrich and color by them later on, so we're going to carry them down. But our embedding is all about these review profile names. And the trick is in our aggregator. What we're going to do is we're going to take all of the unique profile names, we're going to glue them together or pack them together into a space-separated string. This is a big, long string or sentence of the reviewers who reviewed a beer style. Collapses down to our 104 rows again. You can see the interesting row there is review profile list, which is that packed string of reviewers. But I hear you in the audience calling out, John, how does that string help me vectorize, or how does it help me represent my stuff as numbers that you've just represented in a big, long string? Well, count vectorize to the rescue. sklearn has this really wonderful function called count vectorize, which can turn a space-separated or whatever separated string into a big, sparse matrix representation of that string. What it's going to go through is it's going to split the string on spaces, and then it's going to go through and count every one of those tokens. And it's going to make a column for every token that appears in your entire data set. So that is a column for every reviewer who has showed up in beer advocacy reviews. And then it's going to put a little tick of 1 if that beer reviewer reviewed our beer style. And so this is going to build a giant sparse matrix of beer styles by reviewers. And there's going to be lots and lots of reviewers, and most of the entries in this are going to be 0. And so it's a massive sparse matrix. Sparse matrices are ideal because we don't actually write any of those zeros down when we store them in memory. We're only going to store the non-zero entries of the matrix. Okay. Now we have a nice numerical representation of our data, mostly zeros, but some of them are ones. 1 row per beer style, 1 column per reviewer. Our first task has been accomplished. We've represented our data as numbers. Beer styles are a bag of reviewers, and by bag, I just mean unordered collection. All right. Now that we have a representation, we can move on to talking about distance. We need to come up with a good distance across this representation. This is going to be easier in the categorical sense than it was the continuous sense, because there's a lot of less loosey-goosey choices to make from. To answer this question, I'm going to ask you one question about your data. Do counts matter? The answer in this case is counts don't matter. We don't care how often a reviewer reviewed a beer style. We're caring about which unique reviewers reviewed the individual beer style. So our beer styles are sets of reviewers. Sets is just a collection where every element inside it is unique. And for set-based representation, there's a really easy go-to distance measure called Jacquard, which is just looking at the intersection of your two sets divided by the union of your two sets. We're going to move from a Jacquard similarity to a Jacquard distance by doing a 1 minus the intersection over the union. That's fine, but this score is going to be 1 when you have absolutely none of your sets in common. None of your reviewers exist in both beer styles. None of your reviewers reviewed both beer styles. It'll be 0 when all of the reviewers of the one beer style reviewed the other one as well. And so we have a nice distance function over top of sets. Now we've done all the hard work. It's time for the fun part. I run UMAP. I pass in metric equals Jacquard. I get a different embedding. Let's see what this embedding does. This is a very different embedding than the one by rating. This is by reviewers. I'm going to color this one. Good, it's still visible. By popularity, and by popularity I mean the number of reviews of that beer style. And I'm going to play the same hover game as before. I'm going to hover over all the data points and explore them and spend a bunch of time playing in my space. And then I'm going to label this picture so you can see what sort of I came up with. In the bottom left corner here, you have strange brews. These are very odd beers that I had not heard of many of, but it turns out that people who like strange beer styles like all of the strange beer styles, and they go out and try them all. As you wander up along that manifold, you hit wild yeast beers. These are lambics, and these are like Belgian beers with wild yeasts and really powerful flavors that are really nice. You hit up the specialist community there. You can see there are a lot of reviews about those beers, and they're quite close to strange beers because they're not sort of in the common mass market. As you wander down, you hit the lighter beers and the lagers on that blue manifold coming down. And from that, you have 2 paths you can choose. You can either wander through English beers, or you can wander down through Pilsners, and that brings you to European beer styles in sort of the bottom right corner. European beer styles transition up into American IPAs, which are very similar to strong ales and strong IPAs, which are at the very top of your space. And then Belgian beers live off in their own little chunk just to the left of the IPAs. And so you've learned something very quickly about beer styles and how they relate to each other just by embedding these with respect to who reviewed what. So, but what I did was a very general process. Notice I'm doing this on beer styles and not data sets that financial data or malware or anything fun like that. This is in order to remind you that this is all flexible, general, and you can drop in and replace your own data for this data without any problems. I could also just say beers are sets of reviewers, walk through exactly the same process, do a group by, do my count vectorize, assume Jacquard distance, and embed. That gives me this plot for beers or sets of reviewers. I've colored this by brewery. The quick, easy thing to take note of here is that a lot of those colors are fairly cohesive. There are lots and lots of colors because there's lots and lots of breweries, but the cohesion there says, oh, if someone has reviewed a beer from a brewery, they often go out and review all of the other beers from a brewery. They're like, oh, I really like Cascade Brewery. They make fantastic things. I'm going to drink and review all of their beers. And so you get these coherent clusters. You could take that. You can filter again. Oh, but by the way, metric Jacquard, that's where you pass it in the bottom right corner. And you can say, oh, no, I only want the most popular beers. That's great. I go back to my data frame. I filter the beers that have only had 100 reviews. That gives me my popular beers. I embed those into a space. I get exactly the same style of thing. This is popular beer or normal beer. It all comes out. You still have that coherent brewery effect. Which maybe leads you to the next question. What if breweries were sets of reviewers? Do I see a similar effect there? So I take that. I take my distance to be Jacquard. I embed into a space. And I get this lovely embedding here. So this is a two-dimensional space done with UMAP. I've colored the breweries by their number of reviews. Each point is a brewery. Breweries are similar if many of the same people reviewed their beers. You see something that is very common for doing a Jacquard embedding. You see in the center there's this red, very intense group of breweries. These are the very popular breweries that everyone has reviewed. So everyone in the data set has reviewed them, and so they get pulled very, very close together. Massive, extremely popular things. As you wander out, you get into more local geographic areas of your data. And that's because less and less reviewers have done them, and so those reviewers tend to be more concentrated in geographic regions. And you get very fine resolution at the lowest details. In the top left, you have Canadian breweries, which I can do quickly by mousing over and looking at them like, oh, I know that brewery. You get clusters of Vancouver breweries and clusters of Ontario breweries, and so you have a sort of a very, very local extra piece of information contained in the details. From there, you can wander down to European breweries or up to Central American breweries. In the top corner, you have New Zealand and Australian breweries get clustered together because people who review their beers tend to review all of the Australian breweries or all of the New Zealand breweries, and the two review each other's beers a bit as well. And so those partition off into their own chunks. You jump to the other side of that big hub, and you get Midwestern breweries coming down to sort of Colorado breweries. Texas breweries, you can go either Californian, or you can sort of transition down to Southeast breweries. Californian breweries really group up together, and folks really like if I'm in Californian breweries, I tried just the Californian breweries. But they're a little close to the Oregon and Washington State breweries, which also have this sort of, I cluster up together, and which says, oh no, these breweries stick together and people like all of the beers from those regions. If you instead went southeast, you could go down to New York and up to New England and carry on. So amusingly, by examining the structure of breweries with respect to who reviews them, we've learned geographic information about North America, as well as things about sort of brewing culture within North America. So, which is kind of fun. Another twist you can do when you're playing these sort of mouse over games or exploring and embedding is if you're looking at Californian breweries and you find a brewery that is dead set right in the middle of that cluster and is not a Californian brewery, that's maybe interesting. There's maybe a story there, and you can start exploring these things for outliers and what are these things not like the other games, and start seeing what pulled that brewery into that particular region. Okay. This finishes our stories of breweries and how they group geographically. Let's by who reviews them. The next question is maybe, what styles of beers those breweries produce, and that might give a different and interesting lens onto our data. Another way to phrase that is, what if counts did matter? So I'll tell you why. Let's talk about variable link with categorical data, where counts matter, representations. I'm going to say a brewery is a bag of beer styles it makes. But what if many breweries have made most styles of beer over the length of their lifespan? So you've got one brewery that's really well known for its American IPAs, but once in 2003, they made a German double bock. There's another German brewery that makes lots of German double bocks and is well known for it, but once made an American IPA back in 2009. Never did it again. Are those the same breweries, or are they similar breweries? And you might argue, no, they're not. I want to take the distribution of the number of beers they make, or popularity of their beers, into account. To do that, we're going to, instead of saying made or not made, we're going to count the number of reviews each style of beer has for each brewery. All right. Then we're going to pull out count vectorize. It helped us before. Turns out it'll help us again. This is exactly the same thing we did last time. We build that long list of beer styles that the brewery made. We did a group by. We aggregated it together into the space or comma separated list. Then we did a count vectorize. It's not emitting a 1 or a 0 now because we have beer styles showing up many, many times. It's emitting counts of the numbers of times each of those beer styles was reviewed for a given brewery. Now, if we want two breweries that have different popularity to be on the same footing, like we all brew the exact same amounts of beer, but people review your brewery twice as often as mine. We both do IPAs and English porters. If we think those should be on the same foothold, we're going to do an L1 normalization. We're going to divide that row by the sum of the row, and now we have probabilities of making a beer. And the way to think of this is the brewer wakes up in the morning, he rolls a die, and it's like, I'm going to make, American IPAs today. Makes that beer and goes on out. And so this is a vector of probabilities of making a beer style. Now, if we were statisticians, you might, instead of saying that's a vector of probabilities, say that a brewery is a multinomial distribution across our beer style space. That's quite nice, but it's just another way of phrasing the previous statement. We're going to take all of those vectors, or multinomials, we're going to stack them on top of each other, and now we have a matrix of breweries by beer style that takes our counts into account. Now, we need a distance measure on it. That's a representation. And because we're doing unsupervised learning, we need our distance measure to be justifiable and supportable because we don't have labels. But we did just say that each one of those rows is a multinomial over beer style space. So multinomials is stats. I wonder if a statistician can help me. When counts matter, distance. It turns out theoretical statistics to the rescue is something you hear shouted across the hills of LA all the time. I'm absolutely certain. All right. So it turns out in the 50s, they did some theoretical statistics and proved that there is a Fisher information correct distance measure across the parameters of a multinomial distribution. There's a couple of reference papers that are much more modern and easy to read if you would like to delve into that in any more detail. But the cut and the dry of this is it turns out there's a essentially unique Riemannian manifold delta where the points are distributions whose distance function is derived from Fisher information. The metric f on this manifold is called Fisher information metric. You can look at compute geodesics on that manifold, and the multinomial distributions are points along those geodesics. It turns out that if we approximate that with ArcCos, we get a distance called Hellinger distance, and it's a provably correct measuring distance between multinomial distributions. That's very nice. The way to describe that in cartoons is I have two bags of animals, and I'm going to reach into each bag and pull out an animal. And I'm going to count the number of times I see each type of animal. If I can't tell the difference between those bags from the animals I'm pulling out, they are the same bag as far as this multinomial is concerned. And so the amount of information I have lost by using one bag to represent the other bag is the distance between those bags, or multinomials. That is Hellinger distance. Okay, now a brewery is a bag of the beer styles it makes with a distance that's Hellinger, because counts matter. And so now we can look at our data. We do UMAP with metric equals Hellinger in this case instead of metric equals Jacquard. We get this embedding out. We get Gueuses and Lambics, we get Belgians, we get American IPAs in the main cluster. These are, again, breweries that mostly brew those beers. I've colored by your predominant beer style, and it seems to be having a really strong effect. Russian Imperial Stouts are the breweries that brew those, but they also brew lots of Imperial IPAs, so they end up being close together. German beers coming down, we get Czech, you transition into Czech beers, European lagers, and in the bottom cluster you have the American lagers. These are breweries like Coors and Foster's and that style of thing. Okay, this is a very different embedding than our previous geographic-based embedding, but we've learned something about breweries and the styles of beers they make. But where else have I heard of bags of counts before? That sounds really, really familiar. Documents. If you talk to anyone in NLP, they're going to say, oh, I often represent my documents as bags of words. And so if we want to do unsupervised learning on documents, we've got documents are bags of words, and everything we just did applies. So documents are variable width categorical data when counts matter. Representation, this should look very familiar. Very common way to represent a document is a bag of words. More precisely, a bag of counts of those words. We did count vectorize. That's exactly what we did with breweries and bags of beer styles. We normalize those because we want documents of different lengths to be on the same footing. Now we have a document is a bag of probabilities. That's just this multinomial over the word space instead of over the beer style space. That all falls out very naturally. Now a corpus is this document by word matrix with probabilities in there. That's mostly good. The one problem that kicks up here is you notice that when we did the breweries embedding, the predominant beer style that each brewery made had a really big effect at pulling those breweries together. In English or many other languages, you have things called stop words, which are words, or you can think of as beer styles, that pull all of the documents together. And so we really like to correct for that. There are a number of ways to do that via sort of removing expectation, a few other tricks. This is words like if, and, or, those other style stop words. You're going to see lots of them in every document. But a really common thing and an easy thing to do in NLP literature is something called term frequency inverse document frequency. That is, normalize each column by how often that word appears in all of my documents. You can just swap out count vectorizer for TF IDF vectorizer and everything just works from that on. Okay, now we need a distance measure, but I think everyone knows the punchline. I've got a multinomial when counts matter. Well, that document is a bag of words, distance is Hellinger. Everything I just did previously applies here. All of the theory is the same. We have an embedding of documents. Documents are variable with categorical data, with counts matter. We look at our data, we get that explosive picture we had previously. So that in fact was a embedding of documents. Each point there was a document. Two documents are close to each other if they end up using many of the same words in the same proportion. You get clusters of documents in this space. Those are those big, intense yellow bursts, which are documents that are talking about the same thing. Generalizes, though, we could say bigrams instead of documents. That's fine. Instead of words, we say, oh no, order matters a little bit. I'm going to count vectorize with bigrams, and that's two pairs of words that appear next to each other. That gives me a very nice representation. It fragments my space even more, which is a very nice thing to do. That only requires you changing the one line of code in your count vectorizer, which is ngram, to bracket 2, comma 2. All right, that's what we've been calling docmap, i.e. UMAP on documents. But you said all the things. Words are things. How am I going to do this with words? Well, there are lots of ways to embed words into a vector space. Word to vec, glove, fast text, these already exist. What we're looking for is a way to embed words directly into a very low dimensional space in such a way that similar words with similar meanings end up being close together. And you can now visualize and explore those, is what we'd very like to do. Turns out there's a thing called the distributional hypothesis. It was written by a famous linguist named John Firth in the 50s. You shall know a word by the company it keeps. That is to say, don't define a word for me. Show it to me in a whole pile of sentences, and I will extrapolate the meaning of the word from its usage. All right? So a word is a document of all the sentences that contain it, because a document's just a collection of sentences. So if you hand me a whole pile of sentences with a word in it, that's a document. And if I'm going to go sort of standard NLP way, instead of sentences, I might say context, which is, I don't want the whole sentence, I just want the small sub-sentence around that word. That's fine. Or window, that would be another word you could describe the small region around an individual word. You could play kernels over those, and you could do a number of other things that I'm not going to get into in this talk, but they can affect your results when you do this analysis. All right. Word documents are multinomials over the vocabulary. So a word is a document that is multinomial of the words that co-occurred with it in a sentence. Now I've just described this as a problem we've already solved at least twice in this talk. So we can reduce that problem we've already solved. Words are documents, which are variable width categorical data, where counts matter. Word is a bag of nearby words. Distance is Hellinger. We have an embedding. Let's look at our data. This is an embedding of Yelp reviews into the words from Yelp reviews into a two-dimensional space, and you end up having a tremendous amount of your structure actually being preserved there. You have quesadilla, fajitas, taco, you have Mexican food buried down in the very bottom of the space. If you look on the left, you have sashimi, salmon, fish. The whole bottom area is talking about kinds of food. You can move up into drinks on the right. You can move up into regions and places on the upper right. On the up top, you get hipster, pretentious, furnished. You get other things up that way, and so you can wander around your space and you can learn how words are being used in your corpus. And so you've learned not about language in general, but how language is being used within Yelp in this particular case. That's what we've been calling a word map, or UMAP, on words. All right, but we aren't limited to beer or language. We've done all of the hard work. Now we can pivot to lots of fun, different problems. If you liked doing traditional topic modeling, like, I'm going to do LDA or PLSA, I could do that. I can say a document is now a topic. Well, those all generate you multinomials of topics. Wait, I know the distance function on a multinomial. I can use Hellinger distance, and I can embed those into a low-dimensional space in a slightly different way. And these give you documents. Malware is a bag of the commands that it runs when you run it in a virtual machine. This is very general. I run a piece of malware in a virtual machine. I look at the network connections it establishes or the commands that it runs. Each of those is a token or a word. I treat the malware as the sentence that is those. I count vectorize. I UMAP embed with Hellinger. I end up getting an interesting low-dimensional embedding here. This is in fact colored by the antivirus label that you have. You get interesting things. If you notice, there are 3 very distinct red blobs there. They were labeled the same thing by an antivirus piece of software, but they're behaving wildly differently, but consistently amongst themselves when run on machines in a virtual environment. So you found 3 totally different strains of a particular malware, a particular virus, without any labels in a totally unsupervised fashion. Accounts are bags of forums. If you're looking at web forums or Reddits, you could do that sort of thing. You are where you post. Honeypots. If you've got sessions where people log into honeypots and you look at them, you're like, I'm going to look at the series of commands you run when you log on into my honeypot to try to conquer my box. I'm going to describe a session as that sequence of commands you run. I think order might matter a little bit. Okay, I'll look at n-grams or bigrams across that. Bam, I embed it into low-dimensional space. This is colored by the type of virus or malware the individual honeypot session is trying to download to exploit the box. You get a very natural grouping that matches what's actually happening in your data. You could take subreddits. If you wanted to explore all of the subreddits on Reddit, you could say, 2 subreddits are similar if they have the set of users in the same way we had set of reviewers before. And you could explore subreddits to say, these 2 subreddits are really talking about the same thing because they have the same community who really likes them. All right. In other words, insert your thing here is a bag, set, vector, of insert your other thing here. And now you too can go off and embed all of the things. Describe it that way, and you're done. Everything else should just work. All right. You can install the software there. If you're running this in 2019 and not 2020, you're going to have to use the dev version if you would like to have those pretty plots that I've been doing. They're in the 0.4 dev version of UMAP. The installation instructions are there, but they're also the top of every notebook in the repo. Reproducibility matters. That is the GitHub repo where you can download both the talk and all of the notebooks that will allow you to go and embed all your things. Thank you. I have like 40 seconds for questions. Anyone? Wait for the mic.
Thank you, sir. So in a lot of these examples, so for instance, beer reviewers are very subject to fashion. IPA was not fashionable a few years ago, and now it's very fashionable. Malware, you're going to have different levels of attacks that come over time.
Yep.
Like every example that you're giving here, I can easily see wanting to do clustering over time. And a lot of people would immediately jump to cluster by day or cluster by month. But I'm curious to think, like, can you come up with more natural clustering methods? Like, how would you incorporate time into these models and say, like, well, we're going to do a 2-week cluster, and then the trend goes to 6 weeks, and then it goes back to 2 weeks, then 1 week, then 10 weeks. You get what I'm saying?
I totally get what you're saying. And you should come to my PyData talk next year, because that is the current plan for this year. The short answer is the thing we're planning to do next is a regularized UMAP, where I run UMAP in multiple time slices. And I regularize with anchor points between those time slices so that the embeddings line up with each other. And so you can watch your points move through your space over time. And then I've got, essentially, you can see, instead of a 2-dimensional view of the data, I've got a 3-dimensional view of the data that is smooth and meaningful across time, and I can cluster in that space.
So most of your examples were multinomial and towards the end?
Yeah.
Yeah, so are there cases where you had to use other distributions, like some other examples, and then therefore you had to change the distance which you choose and so on?
So in sort of the categorical space, the vast majority of problems we have had are people interested in either set-based or multinomial. And so those are counts matter or counts don't matter. And it has covered more than 90% of the actual use cases that we've encountered with people trying to deal with these problems. But you could do the same thing on other fun distributions. The other tiny use case we have played with is Wasserstein distance across distributions if you didn't have multi-net.
What is the example there? Like, what is the real-world use case?
If you had a time series of data, and it's not categorical, it's now ordinal, because those times matter. So you can look at, in fact, those honeypots and look at when people are doing keystrokes on those. Yeah.
So in all the examples that you've shown, it's appeared to be a 2-dimensional embedding, which is good because then we can actually look at it. Is there anything and I realize part of it is you might be looking for 2-dimensional manifolds. Is there anything inherently saying, 3-dimensional, 4-dimensional?
No.
Okay.
Putting on slides is the only actual difference. If you set n components in UMAP to 20, you embed it into a 20-dimensional manifold. Embedding into a higher dimensional manifold is often useful if you're going to be doing clustering, but not visualization.
Sure.
Yeah.
Great.
I think if there are no other questions, I'm out of time, so thank you again.